At the end of the 19th century, many physicists believed that they were close to a complete understanding of nature. The laws of motion, energy, and electromagnetism had been established, and the universe appeared orderly and predictable. But beneath this confidence, small cracks were beginning to appear. What first seemed like a minor technical problem would soon grow into a major crisis. In this video, we'll explore how that crisis emerged and how a reluctant solution by Max Planck marked the beginning of a new era in physics. By the late 1800s, physics had achieved remarkable success. Newton's laws described motion with precision, and Maxwell's equations unified electricity and magnetism into a single framework. These theories worked so well that many scientists believed the major discoveries had already been made. The remaining work, they thought, would involve refining measurements and filling in the small details. Underlying this confidence was a key assumption that nature is continuous. Energy, motion, and radiation were all believed to vary smoothly, without sudden jumps or breaks. This view would soon change. When objects are heated, they emit radiation. You can see this in everyday life. A piece of metal, when heated, first glows red, then orange, and eventually white as its temperature increases. Scientists studied this behavior carefully. They measured how much energy was emitted at different wavelengths of light for objects at various temperatures. These measurements followed a clear and consistent pattern. The challenge was to explain this pattern using the known laws of physics. At first, this seemed like a routine problem. It was anything but. Using classical physics, scientists attempted to calculate how energy should be distributed across different wavelengths. The result was troubling. The equations predicted that as the wavelength became shorter, moving into the ultraviolet, the emitted energy would increase without limit. In effect, an heated object would increase an infinite amount of energy at high frequencies. This was clearly impossible. Real objects do not behave this way. The theory and the experiment did not agree. This mismatch became known as the ultraviolet catastrophe. It was not a small error or minor correction. The theory failed completely in the region where it should have worked. For physicists, this was deeply troubling. The same principles that explained so much were now producing physically impossible results. Something fundamental was missing. In 1900, Max Planck approached the problem from a different angle. Instead of modifying the existing equations, he introduced a new assumption, one that challenged the traditional view of physics. Planck proposed that energy is not emitted continuously, but in small, discrete units. Planck's idea can be summarized simply. Energy is emitted in discrete packets, each proportional to the frequency of the radiation. These packets would later be called quanta. When Planck applied these assumptions, his equation matched the experimental data perfectly. The ultraviolet catastrophe disappeared. For the first time, theory and observation were in agreement, but at a cost. The long-held belief that nature is continuous had been challenged. Despite the success of his model, Planck himself was uneasy with its implications. He did not believe that energy was truly quantized. Instead, he treated his assumptions as a mathematical tool, a way to make the equations work. There was no clear physical explanation for why energy should behave this way, and the idea remained controversial. Planck's solution marked a turning point. A major problem had been solved, but only by introducing an idea that conflicted with the foundations of classical physics. The assumption of continuity was no longer secure. Without fully realizing it, physics had taken the first step into a new and unfamiliar territory. What began as a technical problem in radiation revealed a deeper issue in the foundations of physics. Planck's reluctant solution introduced the idea that energy comes in discrete units, setting the stage for discoveries that would reshape our understanding of the universe. Thank you for watching, and hope you found this introduction to the birth of quantum theory clear and engaging.